Hello and welcome back. Once again, I'm Dr. Mike, a board-certified radiologist and 3D printing enthusiast. Today, I'm going to show you how to correct severe mesh defects in a bone model generated from a CT scan. This will be in preparation for 3D printing of the bone model. I'll be using the free software programs Blender and Meshmixer in this tutorial. In my last tutorial, I showed you how to remove extraneous mesh within the medullary cavity of a bone. This technique is best used when mesh defects are limited. In instances where mesh defects in a bony model are severe and extensive, a different approach is needed. In this video, I'll show you how to correct extensive mesh errors in a bony anatomic model using Blender and Meshmixer. This assumes that you know how to generate a basic STL file from a CT scan. There are a variety of commercial and freeware products that allow you to do this on a variety of platforms. If you don't yet know how to do this, stay tuned as I have a series of tutorials planned which will show you how to do this on a variety of operating systems and budgets. If you wish to follow along with this tutorial, you can download the free tutorial file pack by clicking the link below this video. This is highly recommended as the files allow you to follow along with the tutorial, which will make learning easier. Included is the STL file used in this tutorial. Also, a powerful Blender script is included which will enable you to easily and efficiently prepare your own bone models for 3D printing. It's a real time saver. If you haven't already registered at embodied.com, registration is free and only takes a moment. Let's start by taking a look at the STL file of the talus fracture in the ankle. This 3D model is from a real patient that has a fracture of the talus. The talus is the bone in the ankle where the tibia or shin bone sits on. The STL file is included in the file pack. Let's open this file in Meshmixer. Meshmixer is free software published by Autodesk, a leading manufacturer of engineering software. You can get Meshmixer at meshmixer.com, where it is downloadable for free. As you can see from this file, once it's opened in Meshmixer, there are numerous red and blue markings which indicate problems with the mesh. If you go to the Analysis section and click on the Inspector button, Meshmixer will automatically identify all the problems that we have with the mesh. These blue balls represent open edges. These are where the tibia and fibula have been cut off by the CT scanner. Red balls indicate non-manifold mesh defects, and the magenta balls indicate areas where there are disconnected mesh pieces. Meshmixer has a feature where you can auto-repair a mesh. So if you click this Auto Repair All button, it will attempt to repair the mesh. Unfortunately, due to the significant number of mesh errors, the auto repair doesn't work properly. You can see that whole bones have been removed and there are large gaping holes within the mesh, and additionally, not all of the mesh errors were successfully repaired. So clearly another approach is going to be needed. Let's go ahead and close out Meshmixer. Let's start by opening this file, which is in the file pack, ankle talus fracture.stl in Blender. If you don't have Blender, you can download it for free at the Blender website, blender.org. Once installed, go ahead and double-click the Blender icon. You can click on the splash screen to remove it. And let's delete the initial cube that's part of every Blender scene. Hit the X key and D for delete. Go to File, Import, STL, and go to the folder that has the STL file that you want. In this case, it'll be the same folder as the file pack that accompanies this video, and select ankle talus fracture.stl. The first thing you'll notice is that you don't see anything. Up here in the upper right, we can see that the ankle talus fracture object is in our scene, but we don't see it. One of the things you have to remember with Blender is that Blender measures distance with an arbitrary unit called a Blender unit. And on the default grid, each one of these small squares represents one Blender unit. Our file is in millimeters, and when Blender imports it, it converts 1 millimeter to 1 Blender unit. So because our file is representing an entire ankle and a foot, it's going to be very, very large, probably 20 or 25 centimeters, which is 200 to 250 millimeters, or 200 to 250 Blender units in size. So we are very, very magged up in order to view our newly imported object. So using the scroll wheel, start to zoom out. Keep going, keep going, and there it is. You can see our ankle object has been imported. One thing you'll notice is that the origin of the object, which is the focus point for moving and rotating, is actually outside of the mesh itself. This can be very irritating because if we're trying to zoom in on an object or rotate and have it orbit, it's sometimes a little difficult to manipulate. So let's recenter the geometry of this ankle onto our origin. Go to the Object menu, select Transform, Geometry to Origin, and now our ankle is centered along the origin of the scene. Next, we're going to inspect this mesh a little bit. We're in solid viewport mode right now. Let's go to wireframe mode. And we're also in object view. Let's go to edit view. And hit the A key to unselect everything. And you can see that there's a lot of extraneous mesh all throughout the bones. For example, in this metatarsal, there's mesh from a medullary cavity. All of these bones have internal mesh components that we don't necessarily want for our final 3D printed model. Also, at the top of the mesh, where the tibia and fibula are cut off, we can see that there are open gaps that we need to deal with. Now, if I want to see how many non-manifold mesh errors there are, I can hit Control, Shift, Alt, and M, and you can see that there are lots and lots and lots of errors in the mesh. Now, removing all of these will be very, very time consuming, especially if you're going to do it manually. You can zoom in, for example, on just some of these, and you can see how complex the mesh is and how difficult it would be to repair all of these defects. Fortunately, there's a way to work our way around this so that we can repair all of these defects within a couple minutes. And I'll show you that a little bit later on in this video. To start with, let's deal with the low-hanging fruit, and we're going to manually close these very large holes that we have at the top of the mesh. Now we can see that the cut lines have gone through the medullary cavity, and we have the excessive medullary mesh that we want to get rid of. So before I close these holes, I'm going to get rid of that. Click on one of the vertices. I'm in vertex selection mode, by the way. Click on one of the vertices and hit Control L to select all connected vertices. And you can see that in this bone, which is the tibia bone, the medullary cavity is conveniently not connected to the rest of the mesh, which allows us to easily delete it. Hit the X key and hit V for vertices, and we'll delete that. There's another small area of mesh that's also touching here. Let's get rid of that. Control L, X, V to delete. Now, in the fibula, it's going to be a little bit more difficult. We can see that there's a mesh that represents a medullary cavity here. I'm going to go to Edge Selection Mode, hit Alt, and select around. This is right-clicking. I'm selecting around this edge. And now what I'm going to do is expand my selection by holding the Control key and the plus button on the number pad. And I'm going to delete by X and V those vertices. Okay, now I'm going to close up these holes. Hold the Alt key down, right-click, hit F to create a face, Control T to convert that face to triangles. And the fibula hole is closed up. Now I'm going to do the same thing for the tibia. Alt, right-click, F for generate a face, Control T converts to triangles. Okay, now let's do something else just that's very, very easy to help clean up our mesh. We'll go to Z, which goes to wireframe mode, and I've selected one vertex. Let's select that vertex and hit Control L to connect all of the adjacent and connected vertices. We can see that these toes are separate from the rest of the mesh. Hold the Shift key down and select one of those vertices, and hold the Shift key down and select another and hit Control L again. I think I've pretty much selected all the mesh that I want to have included in the final model. So I'm going to invert this selection, Control I, and now I've got a whole bunch of extraneous mesh that I can get rid of. So let's get rid of that X and V, and that will delete that stuff. There's still a lot of work to do, but we've cleaned up the mesh just a little bit, and it didn't take too much time. Now let's go back to object mode and hit the Z key to turn off wireframe shading. And at this point, we will I'll show you how to use the shrink wrap modifier to take this a step further. Now, I've been doing 3D printing of anatomic models for about 3 years now, and it took me a lot of time to figure out this trick, so I hope that you'll find this very helpful. Repairing all of these mesh defects is going to be really quite time consuming. It can't be done automatically, and repairing them manually is going to be quite difficult just because of the number of these problems. So the solution to this has been to not repair them. What I'm going to do is, using the shrink wrap modifier, I'm actually going to create a skin that's a separate object from this ankle object, and that skin is what I'm going to 3D print. So how are we going to do this? Well, let's start off with creating a sphere. Go to Add, Mesh, and UV Sphere. And we're going to want our UV sphere to have a lot of detail. So let's crank this up to 256. We'll make 128 rings. And the default diameter or radius of the sphere is 1 millimeter, which is far too small. I want to make this thing gigantic. So let's make this sphere 1,000 millimeters. Okay, so we've got a gigantic sphere. And I'm going to rename this sphere ankle skin, because we're going to shrink it down around our model and turn it into essentially a new object that we can use for 3D printing. The next step is going to be applying the shrink wrap modifier to this sphere. So make sure you have it selected, click on the wrench tab, add modifier, shrink wrap. The target of this modifier is going to be our talus fracture model. The offset, set it to 0.5 and keep above surface. And our sphere has shrunken down to this wedge-shaped object. That's not really what we were hoping for, but it's better than a gigantic sphere. Click Apply. Now, if you apply the shrink wrap object again, or the shrink wrap modifier again, to the same target using the same parameters, it doesn't really do anything. So it would appear as though we've reached the limit of what the shrink wrap modifier can do to our sphere. But that's not entirely the case. Let me close that out. If we look at this sphere and we go to wireframe mode, let's go to edit mode and just take a quick look at it. We can see that the sphere is made of very, very large triangles. And really, given those large triangles, there's only so much that Blender can do in order to fit this around our structure. So in order to alleviate this problem, we apply a remesh modifier. So we'll go to remesh. Want the octree depth to be somewhat high because this is a detailed model. So let's set that to 8. We want smooth for the mode, and we do not want to remove disconnected pieces. Okay, so now our mesh has been subdivided into a bunch of smaller little triangles. Let's apply that. Now if we go to our shrink wrap modifier and try to apply it again using the same parameters, now we've got something that's starting to look a little bit like an ankle. It's not perfect, there's a long way to go, but it's starting to sort of approximate the shape of an ankle. So you can imagine that by repeatedly applying the shrink wrap and remesh modifiers, eventually we can get something that will cover the surface of our ankle model and provide us with a new shell or skin that is free of all these mesh errors and hence more suitable for 3D printing. Let's go ahead and reapply that. So, well, as you can imagine, applying this again and again and again, doing shrink wrap and remesh and shrink wrap and remesh, can be somewhat time consuming. So I've actually written a Python script which will make this a lot more convenient. For those of you who aren't familiar with Python scripting in Blender, don't worry, I'm not particularly familiar with it either, but I have done some programming in the past and it didn't take very long to throw this together. So I've included the Python script in the file pack for you so that you will be able to use it and save a lot of time when you're doing your 3D models. Let's see. Go to the text editor, click Open, and then navigate to the file pack and select shrinkwrap loop.txt. And what we've got here is the Python script that allows you to specify your target, your shrink wrap offset, and the number of iterations that you want to apply the shrink wrap and remesh combination. All of these are embedded within a while loop. So the important thing to remember is that you need to specify your target, and our target is called ankle-talus fracture. So let's go ahead and edit that, -talus fracture. We'll keep our shrink wrap offset at 0.5 and we'll keep our iterations at 20. So it'll go through this 20 times. Let's see what happens when we click on the Run Script button. Okay, I paused my recording for about a minute, which is how long it took the script to run, and you can see that the quality of the mesh in terms of it approximating the anatomy of the ankle bones is significantly better. So that was just executing the script one time. That looks pretty good. There are a few areas where, for example, there's some webbing between the bones of the metatarsals and the toes. And also there's a little bit of webbing here between the distal tibia and fibula. Let's go ahead and apply the script one more time. That'll clean it up just a little bit. Click Run Script again. Okay, so now things are looking a little bit better. Some of those bridges between the toes or the phalanges and metatarsals are now gone. Now I've set the offset at 0.5, so this shell or skin is above the surface of the ankle, the original ankle mesh, by about 0.5 millimeter or so. In order to get down into these little cracks and crevices, I want to reduce that shrink wrap offset. But now that I have a shell that's pretty tightly opposed to the original mesh, it shouldn't be very hard for me to do that. So let me reduce that to 0.3. I'm going to change the iterations to 10. I don't necessarily want it to iterate that many times. And I'm going to run this script one more time. And let's see what happens. Okay, well, now I have a much tighter fitting mesh. You can see that some of the original geometry is starting to peek through. If I go ahead and hide that, you can see where the original surface is starting to come through. But in general, I think this is pretty good. This is a pretty good mesh for 3D printing. The original mesh was actually broken up into several bony pieces. The mesh objects, or the different bones, were not connected. Because we've used a single object at this sphere, and we've essentially shrink wrapped that one object around this entire structure, now our skin, our ankle skin, is one continuous object. So I'm pretty happy with this, and I'm going to go ahead and hide the original mesh. I think this is pretty much ready to export for a little bit of extra cleanup in Meshmixer and then 3D printing. So let's go to the File menu, Export to STL, and I'm going to go to our tutorial files, and I'm going to say ankle corrected in blender.stl. And here's that STL file. I will double click on it and open it in Meshmixer. Now you'll notice that even though we repaired this in Blender, there are still some mesh errors that are present. And this is because of the remesh modifier. The remesh modifier does not necessarily generate manifold output. So it can introduce small mesh errors, actually they're non-manifold mesh errors throughout the model. But the number of errors is significantly reduced. If you look at this model and you compare it to what we started with originally, you can see that our new version has much fewer errors. And these can be easily corrected using the automated protocol in Meshmixer. So click on Analysis, Inspector, Auto Repair All, and boom, your mesh is completely fixed. Done, and we are ready to now export it to a final STL file. Click Export, and I'm going to call this ankle final. And that's that. Your mesh is now ready for 3D printing. Now it may actually be interesting to note that our our mesh that we corrected in Blender is actually better, in my opinion, than the original mesh that we started with. So let me show you what I'm talking about. On the right here is the original mesh of the ankle fracture, and on the left is our mesh that we generated from that sphere, the skin. And you can see that the original mesh was very faceted. It had a rough surface with lots of triangles and polygons that you can easily see is very rough. And our remeshed version is much smoother. So in my opinion, this technique of using shrink wrap and remesh generates output files that are actually superior to the original file that you started with. So not only have you corrected the mesh errors, but you've actually made a surface that's much more realistic. So that's about it for this tutorial. I hope you found it helpful. If you are actively creating 3D printable anatomic models, please consider sharing your work with the Embodied community at embodied.com. That's EMBODI3D.com. Embodied is a community of enthusiasts who are engaged in biomedical 3D printing. You can share your files in the File Vault. If you have questions or comments or wish to share your experiences, you can do so in the forums. Or if you're interested in blogging about your adventures in medical 3D printing, you can start your own blog. Embodied is a community of people who are trying to help each other to do amazing things with biomedical 3D printing. Please consider giving back to the community if you can. Thank you very much. I hope you found this video helpful. Happy 3D printing.